Hi, my name is Dr. Matthew Michal. I'm an adjunct at New Jersey Institute of Technology. I'm going to create a series of video review lectures or reviews on the different topics for differential equations. I used to do these on a different software system, but I will start using these, upload these to YouTube. Hope these are useful. I'm going to start working on where we are currently in the course, or about where we are in the course, and work backwards. So I'll do series and then Laplace, and then work back to those other topics. Hope these are useful, but today I'm going to start on the more difficult topics that we're currently at, on power series, and how it relates to differential equations. So, once again, power series. So, why are we adding yet another thing to memorize? A variation of parameters to specific solution types such as exponentials, polynomials, trigonometric functions, blah, blah, blah. Well, so far we've been dealing mostly with the solutions with constant coefficients. And we're going to need to create another procedure, for lack of a better word, for constructing these fundamental type solutions that don't have constant coefficients. And so when we are left without solution types that we can easily see, series, or more specifically power series, allows us a tool in order to solve these differential equations. And even if we can apply these to solutions we already know. For example, if we see y double prime plus y is equal to 0, obviously we can find out that r is equal to plus or minus I, which is very familiar. That should be sound familiar when we talk about solutions that have trigonometric fundamental sets of solutions. So in the case that I just mentioned, y double prime plus y is equal to 0, we have the solution type of trigonometric functions. Y is equal to c1 cosine plus c2 sine. Well, these solution types will still pop up under our new method. But there will be a lot of these which don't have solutions that are nice and pretty. In fact, different analysts who've studied differential equations have created new types of solutions like the Bessel function or Legendre solutions, where they literally are a series type solution, not as pretty as our trig, cosine, and sine, or our exponential e to the x. But even e to the x and cosine and sine do have their their series form. We talked about that in Calc 2, if you remember. But we're going to, in this video, talk about what does a power series look like, how can we test for convergence to make sure that our solutions actually work on some interval, like we talked about earlier on talking about when do we have solutions for second order systems or higher. But like the undetermined coefficients method, we're going to be solving for individual coefficients. And at the very end, I'll point to you how it's like undetermined coefficients. But we're going to assume that they have a certain solution type, and then see what the solution type actually looks like as a solution. So, power series. A power series around the point x naught has the form of infinite sum. That's that sigma, going from n is equal to 0 to infinity, of a sub n, x minus x naught to the n. In this case, Ran is our coefficient that we're going to end up solving for. Whether that be 1 or 221, we're going to be solving for that. And our x minus x naught is referring to how far am I away from my center x naught. So if I have a point x naught, I'm going to move to the left or to the right from that point. That's what that x comes in. But based on how far away am I affect a certain coefficient an and see what this solution may look like. And we can have the same tests that we deal with in Calc 2, whether they converge or whether they diverge. And so these basic types work just like any other series. But frequently we're going to be using the simplest form, an x to the n, simply because we avoid these messy calculations. And as if you've started working with power series, you've noticed that it's already messy enough. When we deal with our recurrence relations and whatnot, our AN is going to get messy enough. So frequently, we leave it in the basic form where its center is x naught is equal to 0. But we can do it at x naught is equal to pretty much anything under the sun. It'll be dependent on your differential equation, what your x naught will be. But for lack of any other choice, we will frequently choose the easy option, x naught is equal to 0. So, when is it convergence? Well, the ratio test tends to be the nicest. So we're taking the ratio of our next step to our current step to see, is it decreasing fast enough? And it really just ends up working out to, what is this limit of these ANs? And how does it relate to x minus x naught? So this limit of the absolute value of these is just L. And how does that tell us? Well, that L tells us our radius. How far in our radius allows us from our center can we choose x values. So this is our interval of solution, and this is our radius of solution. And simply by finding that value rho from our ratio test, which implies it has to be less than 1, we can solve for that value, that radius value that allows us to find our interval. So, but that allows us to find this whole thing. Remember about whole absolute versus conditional convergence? Because we take our absolute values here, we're taking the absolute value of the series, which implies absolute convergence, absolute value, absolute convergence. And as always, when we're outside this range, we have divergence because rho is greater than 1. So our power series will only converge inside this nice shaded region. So the question is, what happens at that endpoint? Because that's the case when rho is equal to 1, and it doesn't say anything. So we have to use other tests, whether that be the limit comparison, direct comparison, alternating series. Alternating series will be your worst nightmare or your best friend frequently, but this will be the basic of your power series. Use the ratio test for inside, and use another test for the outsides. Frequently, the limit comparison test, the alternating series, or the P series. So, here's the power series. All my ANs are equal to 1, so I have an x naught, which is -1. So, does this converge? Use the ratio test comparing these two values. Well, the limit just ends up being the absolute value of x plus 1 as n goes to infinity. And since none of these depend on n, it's just itself. It's just a constant number. And so the question is when does this absolute value of x plus 1 be less than 1? Well, we return back to your algebra days, to your pre-calc days, and this is the interval from -2 to 0. So inside this range from -2 to 0, from -2 to 0, we have absolute convergence. So now we need to check our two endpoints. So we plug in 0, we plug in -2, and we get, for 0, we get the infinite sum of 1s. And if you add an infinite number of 1s together, you get infinity. So obviously divergent. When I plug in -2, I get an alternating series of -1s. -1 plus 1, -1 plus 1. And we don't know what that converges to, if it converges to anything. So we say it diverges according to the rules set aside in Calc 2. And so since it only converges on our nice little pretty interval, we say it converges on the nice pretty interval. Here's another one. Yeah, more complicated power series. Still use the ratio test. So notice I just plugged in n plus 1 to everything, and I flipped this for a nice pretty cancellation. X minus 1, n plus 1 cancels out with x plus 1 to the n. Oh, that's supposed to be x minus 1 for both. I'm sorry there. So that cancels out to x minus 1 on the top, 3n plus 1 on the bottom, 3n on the bottom, 3n on top, cancels out with a 3 on the bottom. All we have left with as a limit is n over n plus 1, which is just 1, whether we use L'Hopital or we divide top and bottom by n. So we're really saying absolute value of x minus 1 over 3 is less than 1, or absolute value of x minus 1 is less than 3. So our radius is 3, and when we apply it for our interval notation, we get x has to be between -2 and 4. Once again, check your endpoints. Plug in x is equal to -2 and x is equal to 4. Well, when we plug in -2, we get a nice pretty -3 to the n over 3 to the n times n, or the alternating harmonic series. That converges. When I plug in 4, I get 3 to the n over 3 to the n, or 1 over n, because there's still n on the bottom, and that's the harmonic series. Alternating harmonic series converges according to that lovely alternating series test. But this does not. Remember, this is p is equal to 1. That's that divergent case. It's just on the borderline. It barely diverges. Therefore, we do have convergence at -2, but not at 4, so we include the hard bracket on the 2. Lastly, we have a lovely factorial on the bottom, x plus 2 to the n over n. I'm sorry for that awful joke. You're welcome. The ratio test the sucker. We get cancellations. N factorial over n plus 1 factorial ends up with just 1 over n plus 1. X plus 2 to the n plus 1 over x plus 2 to the n just cancels out with the absolute value of x plus 2 on the top. Move it out. So 1 over n plus 1 as n goes to infinity is just 0. Multiplied by 0, well, 0 is always less than 1. And because it's always less than 1, it doesn't matter what value of x is, because remember, we fixed values of x at the very beginning. It doesn't matter, but it doesn't matter what fixed value of x we have. It's always less than 1, according to our ratio test. Because of that, the power series converges over the whole real line, over all real numbers. So we have an infinite radius of convergence. And this really kicks in when we see solutions of the type of cosine, sine, e to the x, sinh, cosh, the whole gambit. So, another one of the things I want you to remember from Calc 2 days are the idea of dummy variables, those dummy parameters on the bottom. It doesn't matter if we have n, k, smiley face, Stanford tree, doesn't matter. They all mean the same thing as long as we have consistent limits. And so this becomes really useful if we need to do our change of variables. For example, if there's an easier way of writing x minus 1, this combination x plus 1, I don't like n minus 1 on the top, even though I have a nice pretty an and a nice pretty limits of integration. I want this to be something, or x plus 1 to the something, a nice linear term, like, say, m. So, let m equal to n minus 1, or the same thing as n is equal to n plus 1. Every time I see an n minus 1, I plug in an n plus m. Every time I see an n, I plug in an m plus 1. So, and for the limits, I plug in when n is equal to 1, m is equal to 1 minus 1, or 0. When n is equal to infinity, m is equal to infinity minus 1, or infinity. And so it doesn't matter. I could have also kept the same variables. I could have said this from n is equal to 1 to infinity of an, x plus 1 to the n minus 1, is equal to n is equal to 0 to infinity a sub n plus 1, x plus 1 to the n. I will do both. I will sometimes change. I will sometimes not. It depends. It all depends on what you're used to, what you're comfortable with. When I can, I'll try to remember to switch, but all that matters is that you're consistent. And you make a clear demarcation of when something happened. When did something change? This becomes also very frequent when I change from n plus 3 that's especially nasty, or I have multiple things going on, I need to make a specific change. And the most frequent thing you will see me do is I want this parentheses. So x plus 1 or x, I will need to make this to some constant or some linear term, whether it be to the m or to the k. That will be almost always be my change variable, to make that some linear term. So choose my k to be n plus 3, or or n is equal to k minus 3, and that changes my n plus 1 to k minus 2, and that changes my n is equal to 0 to k is equal to 3. Because remember, when n is equal to 0, k is equal to 0 plus 3. Okay? Since n is equal to k minus 3, n plus 1 is k minus 3 plus 1, which is k minus 2. Lastly, remember that two power series are only equal if our a_n's are all equal to our b_n's for every value of n in our limit. Why is this important? Remember what I said that I'd mentioned undetermined coefficients earlier? Well, what happens if I have some power series equal to some polynomial, or just some constant 0? Well, we start noticing patterns. Well, this is the infinite polynomial from a constant at 0, so a0 x to the 0, which is just a0, all the way up to, say, a20 x to the 20, plus a21 x to the 21. Well, if I rewrite this polynomial as 1 plus 2x plus 0x squared plus 0x cubed plus 0 and 0 and 0 and 0, that means that the first term in the series is equal to 1. The second a1, or the a1, the second term in the sum, is 2. Well, every other point beyond that, according to method of undetermined coefficients and the like, has to equal to 0, because the only way series are equal is if they share values for our polynomial. Okay? This is series. This is all you basically need to remember about power series. Hope this helps, and welcome to Power Series.